Annyeonghaseyo. Welcome back to Automatic Control Systems lecture. This week we'll be focusing on time domain analysis part 2. In the last class we discussed about basic test signals and we also analyzed the response of first order systems. This week we are going to focus on second order systems. So the step response of the second order systems is what we are going to explore in this lecture. Time response of second order systems. So second order systems are one of the most popular systems. Of all the systems, first order, second order, third order, fifth order, seventh order, 10th order, most important ones are the second order systems. We are going to spend the rest of all our time of automatic control on second order systems. There is a reason why we are going to only focus on second order systems, because second order systems forms the backbone of our control theory. The reason why we only study second order systems is any higher order systems can be approximated as a second order system. Even I have a 10th order system, I can approximate the system as a second order system. Then the accuracy, it depends on several other factors. However, in the real world applications, in many applications, we can accurately model many systems as second order systems. That is the reason why we focus all our attention on second order systems. So in order to explore the time response of a second order systems, we are going to take the DC motor as a good example. DC motor is a fine example and a very well known application. We are going to use the model of the DC motor to explore the second order systems. What you see in this figure is a functional diagram of a DC motor where the load is connected on the right hand side. On the left hand side you see a potentiometer and there is an input device, and then you see an amplifier, you see a motor and a gate train, and the load is connected. So what exactly this one is one of the common functional diagram. However, these days we control with the computer, but this one actually belonged to earlier implementations when the control is done manually. This is a very good example because if you see this potentiometer, these are just resistive circuits. Depending on the position of the arrow, the resistance changes and the output resistance changes. And one of this potentiometer is connected to the load. When the load rotates, depending on the speed, it actually works as a feedback. So depending on the speed, the arrow position changes, and the arrow position changes, voltage changes. And then input is also connected to one of the potentiometer. So if you see this one, if I rotate the input device, I can set manually what is the reference voltage. This reference voltage actually corresponds to output speed. So we can calibrate the speed and then use this voltage as a reference to actually do a speed control. Now when I change this reference voltage, depending on the voltage here and depending on the output speed, the voltage will be different. The difference between the input and output, you see, this is becoming a feedback. Difference between input and output is actually fed back to the amplifier. If you see here, from the input side, then the amplifier, then you have the electrical circuit of the motor. And then based on that voltage, the motor generates the required electromotive force, and based on that you get the torque, then connected to gate train, connected to the load eventually. If you are looking at this one, this is a very nice feedback system which was used several years ago. Then we can use simple equations to model this one and then formulate input output transfer function. In examinations, in many problems, when this kind of system is given, students need not worry about it. What we are going to do is all the equations will be provided. So in one of your assignments or in your examination, you can always see this kind of functional diagrams for control systems, and description equations will be provided. And finally, the students will be asked to develop a block diagram and also find the transfer function. So, you need to understand how this system works in real world and how the energy flow occurs, and then formulate a block diagram and then find the transfer functions. So, in order to build transfer functions or do modeling or analysis, we need to really understand how a system works in the real world. If you understand how the system works, then you will be able to understand the process, build the block diagram, and finally find the transfer functions. So, coming to this specific system here, we have a potentiometer V of t is equal to, so that is the R minus y. You can actually see from the diagram, you can easily observe that V is equal to difference of input, and there is a simple amplifier Kp, R minus y. Motor to load, theta to Va, we already developed this one in the last class. So, you have theta by Va is equal to Kt by Ra, S into Sj plus, this one we already have, and the P constant. Now, we can use this one and actually formulate the system. So, we have this block diagram which we used in the earlier lecture. We can use the same functional block diagram. So, we can take this block diagram and then evaluate the transfer function. So, this is a negative feedback system. So, you can find what is k dash, all the constant, and then g of s we can define as k dash by s into Sj plus B1. So, define new constant k and tau, and then we will be able to simplify the block diagram into a very simple one. So, this forms a simple feedback block diagram, and then we can further simplify it and then get the closed loop transfer function. So, if you look at the closed loop transfer function, what we have is T of is equal to output by input. You have k by T s square tau s square plus s plus k. So, you can further write it in a standard form, which we are going to study later. We can write k by tau s square by 1 by tau s plus k by tau. So, this is something interesting. So, this motor has a nice standard form. This form is what we call a standard second order system form, and this is what our focus will be on for the rest of automatic control. For all the rest of the automatic control, we always use the standard form. Now, what is the standard form? Forget about the motor. Now, let us try to go back to the theoretical standard form. A standard second order system can be expressed as y of s by r of s equal to T of s omega n square by s square plus 2 eta omega n s plus omega n square. Now, this equation, I think this is one of the important equations. I would like to emphasize on that. Okay. So, omega n square by s square 2 eta omega n s plus omega n square. Just use your, we are going to use this reference here, and then this is s square anyway, s square plus 2 eta omega n s plus omega n square. Now, if you see this standard second order system, we have omega n square by s square plus 2 eta omega n s plus omega n square. We are going to work and we are going to focus on this one. You do not need to worry, will be every system we work on will be based on this standard second order system. So, if you are going more into our standard second order system, so what we see is this eta is called damping ratio and omega n is called undamped natural frequency. So, what are these two expressions is that here we have two terms. What I want to define is one is eta and one is omega n. All in these two, in this second order equation, we only have two parameters. If we know eta and omega n, we can actually formulate the standard second order system. So, these parameters define a system. If you know eta and omega n of any system, we have the system model, we have the system transfer function. So, these eta and omega n define or the characteristics of the system. So, in the same way, this below equation s square plus 2 eta omega n s plus omega n square is also called the characteristic equation. So, eta is what we called damping ratio, omega n is called natural frequency. Now, if we try to compare our standard second order system with our motor equation, we can easily find what is eta and omega n. So, when we have a system, we can compare with our formulated system and try to find eta and omega n. So, we can easily find eta and omega n by comparing these two equations. So, by comparing the equation 1 and 2, we get what is eta, what is omega n. So, the transfer function defines a standard second order system. The denominator, as I am explaining you, is what we call characteristic equation. So, this is a second order equation. So, what we call this characteristic equation is s square plus 2 eta omega n s plus omega n is equal to 0, we call characteristic equation, because all the properties of the system are already included in the system. This defines the characteristics of the system, so we call it characteristic equation. So, we take the roots where S1 S2 is equal to eta omega n. So, from the second order system you can easily find the roots. We can use minus b plus or minus b square minus 4ac by 2a. Solve the second order equation, we will get the two roots. These two roots we have minus eta omega n plus or minus j omega n into root of 1 minus eta square. So, if you are looking at these two roots, here what we call alpha a is called alpha is called the damping constant, omega d is called damped natural frequency. You need not worry about the terminology here, we are going to use it so frequently that you will have no problem with them. So, based on the roots of the characteristic equation, we can actually locate them in a complex plane. So, these roots can be complex conjugate roots depending on value of 1 minus eta square. We will have either real part or a negative part. So, based on that we can actually plot them on a complex plane. So, from the characteristic equation we get the two roots. So, a second order system has a second order characteristic equation and we will have two roots. These two roots that are defined by eta and omega n. When the eta and omega n changes, roots change. Roots change, properties of the system changes. Everything changes when eta and omega n changes. That is the reason why we call this one a characteristic equation, and eta and omega n are the main parameters that define the system. So, based on that we can actually plot the roots on a complex plane. So, this eta and omega n determine the nature of the second order response. The effect of eta omega n and omega d on location of roots is illustrated below. So, I try to plot both the roots, and both the roots will be defined based on eta and omega n value. So, this is like a functional diagram where each value of omega n, omega d, omega n into 1 minus eta square are clearly defined. So, based on the values, based on the roots we saw in the previous slide. So, those roots minus eta omega n plus or minus j omega d, we can actually plot them. This is real part, that is imaginary part. You can use the real part alpha omega n and the imaginary part omega n into 1 minus eta square, plot on the complex plane. So, then you have these roots, we can easily define what is theta, what is omega n, what is alpha. So, based on the root locations we have the description here. Then from the roots we can also back calculate all the values. So, if you know the location of the roots, we can even find what is eta omega n, or we can find theta. This theta has much meaning because it defines the damping. Damping is so important because we have not discussed damping. Damping is like absorption of energy. If you remember your suspension system, if you have a good suspension system, when you are actually facing any hump, traveling in a car, the suspension system damps the disturbance or absorbs the energy. So, the purpose of the damping is also the similar in our control systems. Every real systems have this kind of damping effect. So, depending on the location of the roots, your damping will be different according to the system. And then the other term omega n. Omega n is called natural frequency. That means it's more into frequency domain analysis. That means every system's natural frequency will be different. That means if the system's natural frequency is higher, the systems can actually respond to faster changes in the input. Or system speed of the response can be fast. That means when you provide a step input, output can quickly go to the input. So that means your rise time, which we are going to discuss in the later slides, we are going to see how these properties eta and omega n affect the performance. So for the time being, we just need to understand how these parameters are dependent on the location of the roots. So the roots change depending on eta and omega n. So depending on the system, depending on the characteristic equation, we have this kind of roots. That means, for example, I have two systems. I have a Ferrari, I have a Kia Morning, just like we discussed in the last class. Ferrari roots will be different, Kia Morning roots will be different. Ferrari can provide faster response, Kia Morning will only provide slower response. Since the systems are different, properties are different, response will be different, characteristics will be different, eta and omega n will be different, and then location of roots will be different. So for every system, they have a unique location of the roots. The location of the roots define the system. Now let us proceed to analyze the step response characteristics of standard second order system. So now we have a nice standard second order system that is defined as y of s equal to omega n square by s square plus 2 eta omega n s plus omega n square. Now we are analyzing the step response. So we need to multiply the transfer function with the step input. Step input in Laplace domain will be 1 by s, since r of s equal to 1 by s. Now the first case, when we are trying to analyze the step response of a standard second order system, there are three cases, because eta, as we discussed earlier, is what we call damping constant. So eta can be 0, eta can be less than 1, and eta can also be greater than 1. These are three cases. These three cases have different properties. In real world application, if damping is equal to 0, the system can only result in pure oscillations. It's like a spring. When damping is less than 1, it actually have a few oscillations and then come to 1. This is like a suspension in an automotive car, a real car, Jadongja, you have the same suspension. Eta greater than 1 is really difficult to design. These kind of systems are not very common. So of all the system, this system is what we call underdamped system. So underdamped system is one of the most popular, and this almost accounts to 99% of real world system. Most of the systems in real world, we have underdamped systems. Now coming to here, the first case we are going to study undamped, not underdamped, undamped. Undamped means when eta equal to 0. When eta equal to 0, in your characteristic equation will be actually into the form of simple. Your characteristic equation will become s square plus omega n square equal to 0. So you can formulate the roots and then try to get our transfer function y of is equal to omega n square by s into s square plus omega n square. You can actually separate into partial fractions, and then once you separate into partial fractions, I can get the time domain analysis. The time domain is equal to y of t is equal to 1 minus cos omega n t. Y of t is equal to 1 minus cos omega n t. What can we observe here is, if you provide a step input, I am going to get oscillations. That means the sign value only oscillations. So we only get oscillations if the system is undamped. That is the major aspect. The most common and the most popular of all the systems we have is undamped response. Undamped systems accounts for most systems in the real world. So, when I say undamped, eta is less than 1, so we can't ignore eta. So, our y of s will be the full characteristic equation into 1 by s. The roots are in the natural form, eta omega n plus j omega n into 1 minus eta square. Now, I can actually try to break the system into partial fractions, 1 by s minus s plus 2 eta omega n by s plus eta omega n square plus omega n into. So, this expression, if we apply inverse Laplace transform, we get into this complex expression, which is important. We get y of t is equal to 1 minus e power eta omega n t into 1 minus eta square sin of omega n into something. So, this forms our most important response of the system, we call undamped response. Now, students might be wondering, how do we get this expression from here? So, that is the next slide, we are going to really work on it. So, in the next slide, let us see how this is achieved. So, if you look at this expression, y of is equal to 1 by s minus s plus 2 eta omega n, s plus eta omega n square omega into 1 minus eta square. So, if you look at this form, you should be able to recollect our Laplace transform expressions. The first aspect of our Laplace transform expression is sin omega t is equal to omega by s square plus omega square. Cos omega t is s by s square plus omega square. So, if we want to actually transform, the s domain to time domain, we need to change the expression into a form suitable for inverse Laplace transform. So, this is what we have, but if you also remember, if you have an e power minus a t term here, it actually becomes omega by s plus a square plus omega square for sin t and for cos t. What we are going to do is, we are going to actually use this expression and formulate into a suitable form for inverse Laplace transform. So, what I am going to do is, for simpler analysis, I choose a is equal to eta omega n, b is equal to omega n into 1 minus eta square. By doing that one, I can write the expression s plus 2a by s plus a whole square plus b square. We can actually just write in another way, s plus a by s square plus b square by a by b into b by s square plus b square. So, if we look at this expression, I am trying to match to one of this expression. I am trying to match this to one of expression. So, if this is very nice form, so what we can do here is, this form can be directly converted into e power minus a t cos omega t cos b t, and this form can be written as e power minus a t sin b t. So, we can convert directly these terms, and however, I have here a by b. So, I have an a by b. So, what I am going to do is, what is a by b? A by b is equal to, we have eta by root of 1 minus eta square. So, eta by 1 minus eta square. So, if we substitute here, what I get from this expression is, we can write this one s plus a whole square plus b square plus eta by root of 1 minus eta square into b by s plus a whole square plus b square. So, now once I am able to divide the expression into this form, we can actually move the root of 1 minus eta square to the other side. So, I can actually move this one. So, I can write into s plus a by s plus a whole square plus b square plus eta into b by the same expression. So, by doing this one, what I am going to do is define 1 minus eta square is equal to, define 1 minus eta is equal to cos theta. So, 1 minus eta square is equal to sin theta. So, I can write sin theta cos theta. So, if you actually combine, this becomes sine cos cos sine, and then here I have, because we can write the bracket here, I can write 1 by root of 1 minus eta square, and then you can use this expression very similarly and actually transform into this expression s plus 2 eta omega n into this form. So, finally, you get y of t is equal to 1 minus e power eta omega n t by root of 1 minus eta square sin of omega n into 1 minus eta square t plus. So, why I want to tell in a very simpler form, not provide in the slide, is I want students to redo themselves. So, I just give the hint of how to solve, and I want the students to solve the problem themselves. So, if you are really looking, what happened here is, we use this expression and then split into s plus a by s plus a square plus b square and a by b. If you see the a by b, I take a is equal to eta omega n, b is equal to omega n into root of 1 minus h square. Then a by b will become eta by root of 1 minus eta square. So, I get a by s plus a plus b square. So, now I can actually use inverse Laplace transform. This converts into e power minus a t sin b t. This becomes e power minus a t, sorry, this becomes e power minus a t cos b t, this becomes e power minus a t sin b t. And then we can actually, if you read in this form, this becomes sin theta, this becomes cos theta, if you take eta is equal to cos theta. So, if you are looking here, cos eta is equal to cos theta, so sin theta will be root of 1 minus eta square. By taking these two expressions, I can actually inverse Laplace transform, and this will be sin theta cos sin a sin theta cos theta plus cos theta sin theta. So, sin a cos b cos b sin a. So, you can actually use the sin of a plus b, and then e power eta omega t, and you can have this common term here, that is appearing here, and we can take it. So, you can simply, with simple manipulation, you can obtain y of t is equal to 1 minus eta omega n t 1 minus eta square in this one. So, I want you students to actually go through these solutions themselves. Okay, you can use the hint provided here and then do the evaluation yourself. With this one, we actually complete the time domain analysis 2. So, in the next week, we will actually discuss with the time domain analysis 3. So, thank you. End of week 5 part 1. Kamsahamnida.